Now started. Hello. Today we are going to see how the program is executed. Today we are going to see how the program moves from secondary storage to memory and expands in memory for execution. Earlier we have already seen that how the program is built. There are 4 program build stages: the preprocessor, the compiler, assembler, and linker. The preprocessor works on only those lines that starts with hash, produces hello.i. The compiler works on hello.i. It's a GCC compiler, which is a 5-stage 2-pass compiler, which have 5 stages, as you can see here. It prepares the symbol table in first phase and links to all the included libraries. And then the second pass of the compiler will compile the program and produce the assembly code, hello.s. The hello.s will be taken care by the assembler. And finally, it will produce object files, hello.o files, which will be fed to the linker. The linker will collect all the .o files and the libraries, whatever you use in your program, and everything will be linked into one final program. Okay. That is link a.out. Now, when this a.out file, the format of this file is executable linkable format. When this a.out is prepared, this a.out is kept in secondary storage. But when you have to run it, you have to move it to primary memory, from where it will run. Okay. Now, how does this program move from the secondary storage to primary memory for execution? We need to see that. How it moves. Who brings it to the primary memory for execution? Okay. So, let me bring. Now, when you have to bring it from secondary storage to memory for execution, who brings it here? Well, there is a program in operating system. Inside operating system, there is another program called loader. This loader will be used to load the program from secondary storage to memory for execution, and your program will move to memory for execution. When your program will move to memory for execution, then it will expand in memory. Expand. No, it will expand big time. It will expand in memory. The expanded space that you see here, let me put some light color. This expanded space that you see here, the expanded space is called process context or process context, virtual address space, process context. See, this is important for you to understand everything which I'm telling you. If you feel there is any doubt, ask me immediately. But this is important to understand, because when you go for C interview, if you will go for the first job or you are changing your domain, so people will ask you this. Okay. So this is called process context, and another name for this is virtual address space. And you'll need to know this. Without this, it will be difficult to do development for systems, and debugging will also. So this expanded space is called process context and virtual address space. This is a big space. It's a big space. Where's my line one? Yeah. So this big space goes from top to bottom. The size of this big space is, you'll understand why I'm saying big, because it is really big. You know how big? The size of this space is staggering. Staggering, huge. This is 64 GB. Isn't it really big? Yes, it is really big. Now, question. You have only 4 GB of RAM, suppose. In 4 GB of RAM, how will you store 64 GB of process address space? Over that, there are hundreds of processes executing in your system. How will you store space, no, hundreds of, maybe 100 processes in your 4 GB RAM, where every process have a process context of 64 GB size? Well, this is really very nicely done in our systems. When I say 64 GB, what is 64 GB? Memory? No, it is not 64 GB of memory. Actually, it is 64 GB of addresses. 64 GB of addresses, not 64 GB of memory. So that's true. 64 GB of addresses. It is 64 GB of addresses. These addresses may most of the time not have associated memory locations. Okay, memory locations may not be there, but 64 GB of addresses will be there. These addresses are called logical addresses. Logical addresses. Okay. So you understand what is a logical address? Keep it remembered, memorized all the time. Logical address. So this 64 GB what you see are actually 64 GB of addresses. But these addresses may not have location. Maybe RAM is only 4 GB, and out of 4 GB, maybe few half of GB is available for you for execution. So how does 64 GB of addresses use that memory? Let's draw an analogy to understand this. Suppose you have a rope that is 20 meters long, 20-meter long rope. Okay. Now that 20-meter long rope, you have a pipe only 1 meter. There is a pipe of length 1 meter. Will you be able to pass that 20-meter rope through that 1 meter pipe? Will you be able to pass that 20-meter rope through 1 meter pipe? Huh? Ah, you can. Give me the gestures at least. Okay. Now, similarly, like you can pull the rope through the pipe or complete 20 meters. Similarly, you can have 64 GB of process that could pass through 4 GB of RAM. Okay. But these are only 64 GB of addresses. Now, suppose the length of the rope, listen carefully, the length of the rope is 20 meters. So there is the first meter, second meter, third meter, 10th meter, 15th meter, and 20th meter in the rope. So these lengths, 1 meter, 5 meter, 10 meter, these are logical addresses. The actual 1 meter of the pipe is like actual physical addresses. Suppose the third meter of the rope is in the pipe at this moment. So third meter of the rope is mapped to 1 meter of pipe. Then you pull little more, you have the fifth meter of pipe, fifth meter of rope in the 1 meter of pipe. Then you pull a little bit more, sixth meter of rope in the pipe. This is how logical address and physical addresses will be used. Every time more process will execute, more code will go in the memory. So you will have the logical address of the code translated to the physical address of the memory, like the 7th meter of the rope was in the 1 meter of pipe. Similarly, some logical address out of 64 GB will be in available physical addresses. So logical to physical address translation will be done every time the code will execute. This will discuss in system programming. Okay. So this virtual address space is further divided into 4 segments. There are 4 segments inside virtual address space. 4 segments. These 4 segments are: first, stack segment. There's a very good understanding you need about the stack segment. What is stack segment? How it works? A very good understanding is needed. Without this understanding, it will be very difficult for you to put in system programming, network programming. Second is libraries segment. Third, then you have is data segment. And the last segment is called code segment, which is absolutely adjacent to this. Code segment where you'll have your compiled code. Okay. So these are the 4 segments. So one more thing I want to tell you right now before we do anything else in this. The beginning of code segment. This. Where does the code segment begin? Is an important question. And the answer to this is very strange. The code segment, when we start looking at the process context, we look from the bottom to top. Okay. The code segment that you see here, let me tell you what this code segment. I hope everybody have linked to this T.02.001, T.02.001. This is the beginning of code segment. The code segment never starts from any fixed address or location. The beginning position of the code segment is randomized using an algorithm called address space randomization algorithm. Okay, address space randomization algorithm. So this algorithm is in Linux, and this algorithm ensures that the starting position of the code segment is always randomized. This is a security feature. It is because of randomized position, nobody is able to depict that where there's a code segment starts. So it becomes very difficult for the hackers to hack it. Okay. Now, why do we need stack segment? Stack segment is used for what purpose? Stack segment. Used to store local variables. You know what are local variables? The variables that you declare inside function. The variables that you declared is, suppose you have a main function. Inside main you declare int a. So that int a will become local variable. But if you declare that variable outside main, so that will become what?
Global variable.
Global variable.
Manish, did you understand? That the variable declared outside main is called global variable. But if you declare a variable inside main function, for example, suppose you write a program It's hello.c. Inside this program, suppose you write your program like this: hash include stdio dot h int name return 0. You declare variable here int I. So because this variable is declared inside main function, this will be called local variable, and this local variable is called local variable because it could be used only and only inside main function. It could be used only inside main function. Line number 4, 5, 6, 7. That's all. If I declare a variable here, int g, so this is a global variable. It could be used in any function. Okay. Main के अलावा there will be more functions, so you can use it in every function. Okay. So the local variables like int I are stored in stack segment, used to store local variables. Then you have now this is about library segment. Used to provide libraries. Just say, for example, we have used printf, scanf, sqrt, math libraries. So all the libraries that will be provided to your program at the time of execution will be provided through library segment. We'll see how these will be provided. Used to provide library segment. It have three more sections. It have three sections. Library segment have three sections that are shared libraries. Then you have dynamic libraries and dynamically linked libraries basically, and statically linked libraries. So these are the three types of libraries we have. So three sections we have in library segment. I will elaborate it later. Then comes data segment. Data segment is another very interesting segment and very useful. Data segment used to for different purposes. Used for dynamic memory allocation. Okay, whenever you do dynamic memory allocation using malloc and all these things, so you'll find all these memory allocated here using heap. Not the dynamically allocated memory is kept in heap, that I'll describe you later. It is also used for global variables that are initialized. Global variables that are initialized with some data. It is also used to keep global variables that are uninitialized. Both type of variables will have. It is also used to keep static variables. It is also used to keep register variables. It is also used to keep volatile variables. Then it is also used to keep macros. It is also used to keep constants and qualifiers. It is also used to keep pre-processor directives. So all these things you will find in the data segment. Finally, you have code segment in which you have your compiled code. There is no need to write. Everything clear? Any doubts till now? Okay. Other than this, if you have doubt, please ping me immediately. Okay. Other than this, it have this set of file descriptors, 3 file descriptors. These 3 file descriptors. File descriptor number 0 and 1 and 2. These 3 file descriptors are connected to some input-output streams. Suppose these are some streams out there. These are connected to streams. Standard output stream, for sending output. Then you have a standard error stream for reporting errors. Then you'll have standard input stream for taking input. These 3 streams you'll have always. Now, what are these streams? Streams are logical data channels, okay, which are used to send and receive data in and out of your programs. So you'll have 3 streams here. STDIN, a stream to take input into your program. All the input will come into your program using standard input stream only, STDIN. Then you have another stream called standard STD out. All the data will be sent out of your program, STDOUT, using standard output stream. And you have a third one, which is here, which is STDERR, standard error stream. All the errors will be reported using STDER. Now, when you do scanf, you are reading data, isn't it? So data is coming into in your process. So data will come through standard input stream. When you're doing printf, data is going out of your program. So you'll use standard output stream. All the errors will be reported through file descriptor number 2. This file descriptor number 2 is connected to standard error stream. Okay. So these 3 are called file descriptors. File descriptors. File descriptor number 0 and 1 and 2. All three are created in your process right in the beginning when your process is created. So these are default file descriptors. This will always be in your process context. Other than that, inside the process context, you have some tables, like memory descriptor table, symbol table, like this. You'll have some tables also. Those tables we'll explore later. There's some tables you will have, very useful tables. Some tables, quite a few number of tables. So one by one, we'll see those tables. Some table. This I'll tell you later. What are these tables and why these are there? So this is the process context that is created whenever you execute your program. Okay. Now, there is one more thing other than that, other than the whole process context that is created. That another thing that is created is called task structure. In Unix world, it is called, and in the theoretical world, it is called process control flow. In Linux, it is called task underscore struct. Okay, this is a kernel data structure. It keeps all the information about the process. What all things your process have, what all things your process, okay, all the attributes and metadata about your process, everything is maintained by the process control block. Like it will contain things like process ID, parent process ID, who created it, flags, status, blah, blah, blah. So much information it will have. Program counter, which keeps track of which statement is going to execute next. All these things are maintained by the operating system, Linux, about your executing process, and is maintained through process control block, which is also called task struct. I'll show you this task struct. Hold on, see. Let us go inside kernel. CD USR SRC Linux version that I have. Inside this, you go to include Linux directory. Here you have a header file called sked.h. Inside it is used to define struct task struct. This is what I am talking about. There it is. See what kind of abundance of information it will keep about your executing process. Process have created some thread. There is the thread information, state of the process, saved state. This is a pointer to the beginning of the stack segment. Usage statistics, flags, process trace, allocation tags, on which CPU core this program is executing, on which this process is loaded and is executing on which CPU core. Some wake-up entries. I'll list only those things which will be able to understand right now. The priority, static priority, normal priority, real-time priority. Then what are the scheduling entities? And then information about so much of information. Stats about statistics about the program, executing program. Then what is the scheduling policy? And the associated information. Read copy updates. Task tracers. the scheduling information, and active These two are pointers. Both are pointed to beginning of process context. So there are two pointers basically, star and another is active star active So these are the two pointers which points to the beginning of the process context, and the process context actually starting address of the process context is kept here. Okay, then the exit status, exit code, exit signal, then scheduling information. Then you have information about these things. I'm not telling you because you have not understood it yet. The process ID, the thread group ID, if you have created thread. Then who parent? There are two type of parents. I told you parent, PPID, ID of the parent. Actually, there are two type of parents. One is real parent, another is foster parent. Okay. Then your process may have created more processes, children. Okay, your process may have siblings. Your parent may have created 10 processes, all are siblings. Who is the group leader among them? Usage time, system time, starting time, process credentials, name of the process. Your process is executing in RAM, memory, and there are files kept in secondary storage, other files. Your process can access those files using these things. Okay, so see, so much of information you have. Interrupts, hardware interrupts, software interrupts, IRQs may be used by your program. Block IO for large amount of data transfer. So much. If you're using NUMA architecture of the processor for digital videos and streams, then the NUMA architecture, if used, will be mentioned here, otherwise it will be null. There's so much of information, abundance of every field is initialized, and throughout this training we'll keep on learning this, and a time will come that we will know everything that is there in this. So much of abundance of information till here. So this process context, this task structure is what I showed you inside kernel. One day you and me will sit together here and you will be coding it. Okay. Now this task structure is maintained by Linux for every process. And you know how many processes are executing right now? PS-all executing. PS-all executing processes. So many processes are running. This is a process ID of every process. So many processes are running in our system right now. Running. Okay, and every process have process context. Also, every process have task structure. So huge amount of activities going on behind the system. Linux system is so actively involved in maintaining how our program is running. You getting it? Okay. Any questions you have regarding this? If thumbs up means all is well. Otherwise, you ask your question. Okay. Keep responding. Okay. Now let's pick one of these segments to understand all the three segments: stack segment, library segment, data segment. We have to study. Okay. Then this file descriptor table also we have to study, and this task structure also we have to study. We'll start with, and these tables, one or two tables I'll tell you. Let's start with stack segment. What is this stack segment and how it is implemented? Elaborating stack segment. What happens in your here in the stack segment is, suppose you write some code, simple code that I showed you just now. Yeah, this. You write this code. I will remove these comments. This is a simple code you have written. You have declared a variable called int I. Okay. The moment you see this opening flower bracket, that means function have started. So inside your stack segment, a stack would be created. Stack created. Inside the stack segment, a stack is created. The moment this opening flower bracket is encountered, explaining that some data is going to come. So a stack is created. Stack. Inside the stack, you'll have entry that, okay, main function have started. Okay, here comes the entry. Main function have started. So you have entry about main function. The moment the main function starts, a stack frame is created. Stack frame is another kind of organized buffer that is accessed through stack. Accessed through stack. So this main is now connected to the stack frame. The stack frame will contain some data. Data that is associated with your main function. We have created int I. So there will be an entry about I. Do you have any value in there? Well, if not now, so you don't have any value, you don't mention any value. But yes, one int I variable is created and is kept inside your stack frame. So all the data that is associated with main function, that is local to main function. Int I is local variable, local data will be stored here. When you give some value, you'll have value also. Now suppose later on you say here I is equal to 5. So you have given data to 5, isn't it? So now your I have data. So you'll have I is equal to 5 data in here now. So like this, stack frames are used. If you declare a global variable will not come in. If you declare another variable, suppose you declare another variable, comma j, then you'll have another entry here in the stack frame about j. And if you want to give some value to j, you can give value. Suppose you give value to j6 in your code like this. J is equal to 6. So like this stack frame will be created, and this is how the stack is organized. It is important for you to know that when you're creating variables, where are these variables going? Where are these variables getting stored? You will have many functions like this. Suppose you have another function in your same program. Another. The name of the another function is another. Okay. So you'll have another stack frame created exclusively for the other function. You'll be connecting to the other one here like this. If it will have its own local variables, we will have a list of its own variables. This is how the whole stack segment is arranged. Okay. If you have any questions, you can ask me now. A stack segment. This knowledge is very important before you start coding, because when you create variables, you should know where your variable is going. How will you define the scope, isn't it? When the function will be over, the stack frame will be destroyed. That's why the local variables are destroyed. Now, when you go for some little senior level, they will not ask you what is local variable. They will ask you why the local variable is local and why the local variable is destroyed after the function is over. We will explain this. Like, right? So that's all I have for you today. And if you have any questions, you can ask me now. Or you can ask your questions in the discussion forum also later on. Thank you.